Let's make let's make a start. So thanks everyone for coming. It's a great pleasure to have Ben Yee here from the Curtin Centre for Optimisation and Decision Science. Ben's got a PhD in engineering from ANU in 2018. He postdoced in the University of Groningen in the Netherlands on networks and robotics. And he has been a member of the Optus Curtin Centre of Excellence in Artificial Intelligence from 2020 as an Optus Research Fellow. And from there won the WA Premier's Early to Mid-Career Research Fellow Award, which he now holds, which funds him as a member of the School of Electrical Engineering, Computer and Mathematical Sciences. I know Ben through various dalliances with Defence and DSTG on the topic of his talk today on complex network models for the spread of social contagion. It's a real thrill and pleasure to have him here. So thank you very much for coming and talking to us, and take it away.
All right, yeah, so good morning, everyone. My name is Ben, as Lewis mentioned, and today I'll be talking a bit about research that's gone on for the last 5 years or so, starting from my postdoc. So first, I'd like to thank Lewis for inviting me here and allowing me to share my research with you. And to my collaborators, in particular, Lorenzo, who's an assistant professor in Turin at the moment. I refer to him as my Italian twin because for everything that I talk about today, he's really been working with me very closely. Ming was my postdoc advisor, and he kind of nurtured this interest in going beyond just theoretical mathematical analysis and doing experiments, working with data and so on. Roy's a PhD student, and I think some of you will know Nick and Bradley, who I've recently been collaborating a lot with. Besides that, there's other people, of course, that I've had the pleasure to work with. And funding from the WA government's kept me going for the last couple of years. So what would I like to do today? I'd like to introduce to you a network model for how social contagion spreads. It's a very abstract model to begin with. And then I'm going to talk about its application in particular to social convention change. That will be the first part, and we'll sort of do a deeper dive, go into a bit more technical aspects. And then in the second half, I'll present at a high level the different ways that we can use this type of network model or variants of it to study social contagion spread in different contexts. If you're interested, the papers that my talk is based on are shown here, and I'm more than happy to share them with you if you're interested in the details later. So this is how I'm going to break out my talk. I'll first talk about social contagion in an abstract sense. The model that I'm going to pick is based on game theory. Then I'll do this, as I mentioned, a closer study of social convention change and look at some different problems. So this is an example of social convention change and contagion spread that everyone experienced over the last couple of years during COVID. We went from primarily greeting each other by shaking hands to suddenly elbow bumping, maybe in some instances, or bumping fists. And then, of course, today I greeted Lewis with handshaking. So there was change to something else and then change back in terms of social conventions. So broadly speaking, what I'm interested in is the spread of some contagion, which can be thought of as a novel behavior, idea, or product that spreads across a population and in some cases replaces some status quo. So here, novel doesn't necessarily mean it's completely new. It just means it's new to the population that we're interested in studying. And the spread of contagion is often driven by the way people interact and make decisions at an individual level, just like every time we see someone, we decide whether to shake hands or to bump elbows. But nonetheless, then we have collective phenomena emerging where we can have large changes in the way entire populations behave if these interactions move in a particular direction over time. And of course, it's of primary interest because when there's quote unquote a positive contagion that spreads, then we have growth and improvement across society. But when there's some negative contagion like misinformation, we can get serious societal harm. Here is one of the most classical examples of, let's say, contagion spread in a population. Ryan and Gross in the 40s looked at how hybrid seed corn, some new corn breed, spread in Iowa farming communities, and they collected empirical data on the uptake of this new corn. So on the x-axis, you've got the time, and in the y-axis, you've got the percentage of the farmers adopting this new corn. You can see that there was, or that this shape is an S-shaped curve. So in diffusion literature or in contagion spread literature, there's often reference to the S-shaped diffusion curve, which you'll see a couple of times during today's talk. But some properties of this curve, there's a delay often, sometimes short, sometimes there's none, but oftentimes there's also a reasonably long delay between when the contagion is first introduced until some tipping point or the contagion process takes off. And then there's a transition from 0 to 100% adoption of the contagion of interest. And this can be sometimes short and very explosive if something's gone viral, but other times it might be quite drawn out. The driving forces of contagion spread are many, and here are the three, I guess, sort of most important ones, or at least the most prominent ones. We could have a committed minority of people who are really trying to champion this particular contagion. They go about promoting it, they really try and visibly adopt it at every possible instance. Sometimes the new contagion or the innovation is superior. So in this case, this new seed corn provided better properties than existing ones. And so that might be a driving force for contagion spread. And in other cases, authorities might decide to enact legislation to push through something new. I'll mainly focus on the top one and touch briefly on the second one, but I won't go in, well, I haven't done any work on the third one, so I can't really comment. Okay, so now that we've got some understanding at a sort of abstract level of the problem of interest, let me go into the way we approach the mathematical modeling. So we take a game theoretic approach where we've got a population of agents. So sometimes we call this an agent-based model. And these agents represent individuals in the population. So we're going to denote this population by V, and we arbitrarily label the agents 1, 2, all the way through to N. They interact over some network, which this network represents some abstract form of social interaction. And at discrete time instance t, from 0, 1, 2, all the way through to infinity, agent I in the population, so any arbitrary agent, can select between two alternative strategies. And we denote the ith agent strategy choice at time t by x sub I. And so 0 is one strategy and 1 is the other strategy. We've got some binary choice. So here's a very simple example of, let's say, a network or a view of the model. I'm going to look at it from the perspective of the center node. And in game theory, you have a payoff function. So that determines how the agents are rewarded for selecting the different types of strategies. So the payoff functions are denoted by pi. And there's a function for selecting strategy, there's a payoff function for selecting strategy 1 and a payoff function for selecting strategy 0. And the way that the payoff works is the payoff for selecting strategy 1 from the perspective of the center node is equal to the sum of xj times 1 plus alpha, where j is the neighbor set of agent I. So the way we intuitively interpret this is that xj counts the number of your neighbors picking strategy 1, or the red strategy. So in this case, there are 4 agents that are the neighbors picking strategy 1. So the payoff is equal to 4 times 1 plus alpha. I'll get to what this alpha means in a second. The payoff function for strategy 0 is 1 minus xj. So this simply tells us the number of neighbors who are picking the blue strategy or the 0 strategy. So in this case, they get the center agent will get a payoff of 1 if they pick the blue strategy. Alpha is some coefficient between -1 and infinity, and it captures the relative advantage or disadvantage of the red strategy over the blue strategy. So when alpha is 0, every neighbor provides you with the same reward whether you pick blue or red. If alpha is negative, then this is less than 1. So you get per unit lower payoff for selecting the red strategy. And if alpha is positive, then you get a higher reward for picking the red strategy per neighbor that's picking the red. And what we typically assume is that strategy 1 is the contagion. And actually this is a typo, it should read 0. So 0 is the status quo. So we're interested in often what happens when you have a population of blue or agents that are initially picking blue, and we introduce some red into the population. Will this strategy spread over time? So in game theory, there are payoffs, and then there's also a way for the agents to revise their strategy selection process, and that's what we'll talk about now. It's probably not too, far of a stretch to assume that we're dealing with mostly rational agents here, and if you're rational, you typically want to maximize the payoff for whatever game that you're playing. So in game theory, this is the simplest version of this is called myopic best response. It means that the agent cares only about maximizing their immediate payoff. They don't care about investing into the future or planning ahead. What is happening right now is what they want to maximize in terms of strategy selection choice. So quite simply, that means at the next time step, agent I will select strategy 1 if the payoff for 1 is greater than the payoff for 0. And they'll select strategy 0 if the payoff for strategy 1 is less than or equal to the payoff for strategy 0. So it's very intuitive. You can also introduce some sort of stochasticity into the model. And this might be to try and capture the idea of bounded rationality, the idea that people typically want to improve their payoff or their position, but every now and then they might actually do the opposite. So they might select the strategy that gives the lower payoff, sometimes for, or just to account for randomness in the way people behave. So the details of this is known as log linear learning, but what it really says is that the probability for selecting strategy S is given by some formula here, where we've got an exponential term, the payoff functions, and a coefficient beta that's between 0 and infinity, and it captures an individual's level of rationality. So when beta is equal to 0, it's a coin flip. There's a 50-50 chance that this agent's going to select blue or red. On the other hand, here's a plot of the difference in the payoff between the strategy 1 and strategy 0, or agent I. And the higher the rationality, the more likely it is, the higher the probability the agent will choose the payoff that gives the strategy that gives the higher reward. And when there's a lower rationality, then this probability gets lower and lower until it becomes, as I mentioned, a 50-50 chance. So another way to think about this model is to think of it as a complex contagion effect. The fact that I said complex contagion suggests that there's also something known as a simple contagion, which I'll get into at the end of the talk. But for now, it suffices to explain what a complex contagion is. It's the idea that the effect of your neighbors, so the way your neighbors influence you, is not independent of one another. And the easiest way to understand this is to look at the probability that the center node is going to adopt the red strategy, or the contagion, as a function of the proportion of neighbors who have already adopted the red strategy. And so here's an example of a curve where even up to about 30 to 40% of your neighbors selecting the red strategy, the probability of selecting red for this center agent is quite small. And then all of a sudden, when you cross some magic threshold, let's say 50% here, that probability increases rapidly until it reaches 100%. So this is just another interpretation of this game theoretic formulation I've just talked about. What you're really saying is when enough of your neighbors have adopted red, you will also switch to red. And when enough of your neighbors are adopting blue, you will switch to blue. And there's a sharp increase in the probability at some middle point.
Sorry, there was one thing that I missed. So on the previous slide, you've got these sort of decisions that are based on the payoffs, the pies.
Yeah.
Are those the pies from the previous time step t, or?
Oh, yes. Sorry, yeah, it is from the previous time step t. So
you're always looking back at basing it on history and then predicting what you're going to do.
Yes, but exactly just one step behind. So you're not looking at the, let's say, the history of all past decisions. It's just the exact decision. Yeah. So it's a Markov process. Okay. So that's a lot of let's say jargon. Let's go into a simulation to look at an example. I've just created some synthetic network structure and populated the red and blue strategies randomly through the agents. And the only difference here is, in this case, the red and blue strategies are equivalent. And on the right-hand side, the red strategy is a slight bit better than the blue one. So what you see in the on the left-hand side is the formation of clusters of red and blue, which depends on the network topology. And so this kind of captures, let's say, a common observation in social networks, which is strong local conformity and diverse global patterns. But when alpha is positive, you can see actually that over time, the red contagion in this case actually successfully spreads across the entire network. And probably won't surprise you, but the larger is alpha, the faster is the spread of this contagion. So there's a lot of work devoted to how fast the contagion spreads as a function of alpha. All right. Okay, so hopefully that gives you some introduction to a game theoretic approach to social contagion modeling. And now I'm going to look specifically at social convention change as an application for that model I just talked about. All right, so social conventions are generally agreed upon behaviours, standards, or customs. So you can think of, for example, which side of the escalator you stand on. Of course, it's the left-hand side here, but anyone who's spent time in Europe knows it's the right for most countries in Europe. Greeting conventions, which I've already given an example of, the way that we greet each other depends on which country, and sometimes, as I mentioned, the time in which or the period during which this occurs. And another very popular example that's used is language convention. So the way we spell words changes both in terms of, let's say, past history and also geographical location. And even the same word can have different meaning depending on whether you live in the US or in Australia. And the key characteristics of social conventions which kind of motivate the game theoretic approach is that there are many alternative choices and many are generally equivalent. So whether you shake hands or elbow bump, I mean, maybe there's a small hygiene advantage which is no longer as relevant now, but more or less you could do both and you get the same outcome. The main benefit comes from people coordinating. So in that game theoretic model, you typically want to coordinate with the most dominant strategy in your neighborhood. And so this is one reason why we selected for social convention modeling. Again, it doesn't matter if you spell color with a U or without, as long as everyone's consistent and we understand what it means. And the last one is something which we already briefly talked about in the previous slide. Conventions remain the same for long periods, but then can suddenly change. And so this new convention often spread like a contagion. And that's the last, I guess, point about why we're interested in social convention change. So the way we approached it was to run a set of multi-round group experiments that tried to replicate social convention change. And then we used that experimental data to develop and further refine the agent-based model. So the way we did that was to recruit between 12 and 16 people, and we asked them to imagine they were on the board of a company who were tasked to launch a product or two alternative products, one called Tau and one called Eta. And you could vote over multiple rounds, and after each round, you could see the fraction of the other people in the game that had voted for Eta and Tau. So here's an example where the player sees 30% have voted for Tau, 70% have voted for Eta. You have a chance to revise your decision in the next round. And at the end of each, okay, so just explain that. The game stops when a consensus is reached. So every player in the game votes for the same product. That means the company successfully made a decision, product gets launched, everyone gets paid. Or after 24 rounds, no consensus is reached, the game stops, no one gets paid. And what we did was to introduce a number of committed minority computer bots into the game so that when the human players mostly converged, for example, on the Eta product, we suddenly introduced, without them knowing, these computer bots that would vote for Tau to see whether or not they could overturn the established status quo, which was Eta, and to force the human players to convert to Tau, because that was the only way they could get paid, right? So they have to reach a consensus, which means they have to side with the bots if they want to win money. And here's an example of 3 different trials that we ran. So we ran 20 in total with 180 participants. And in most of the trials, I think about 40%, we saw an almost immediate diffusion from the status quo to siding with the bots. In other cases, I think about 30% of the time, we saw a delay, sometimes up to 10, 15 rounds, and then a very rapid conversion to siding with the bots. And in other times, trials failed to reach a consensus at all, and so no one got paid. And that happened more often than we expected, given we assumed people liked money. So we also conducted in-person trials where we actually sat people in a room like this, and so they could play seeing each other, and we even added name tags in front of them so that they could see who was voting for what, to try and look at whether identifiability, for example, had an effect. So this is group level data. And the next thing we did was look at the individual level data, and in particular, we zoomed in on the way.
Sorry, one question. We were the 180 participants in 20 groups. That's like 9 people per trial. Was that sort of roughly what the number of true people were and the rest were bots?
Yeah, so the number of human players ranged from 8 to 10, okay. And the bots always filled up the gap to make it 12.
Okay, so no repeats in particular, right?
Yeah, no. Yeah.
How come the proportion started at 0? Did they...
Oh, so this is to show after the status quo has been reached. So they sometimes play a couple of rounds before this, where the human players get to vote, and if there are only humans, they very quickly reach the same status quo. So there'll be Eta in this case. And then after the humans have, the human players have reached consensus, the computer bots suddenly appear without them realizing.
And this is fraction of human participants?
Yes, yes. So here is, the particular thing we're interested in from the individual level data was how often players changed their strategy during the duration of the game. And so here's a frequency plot of the players and the rate at which they switched, or the fraction over the entire game that they decided to change strategy, whatever that strategy might be. So it's quite noticeable that there's a huge heterogeneity. There are a couple of players that switched almost every 3rd or more rounds. And then also over 50% of the players actually just changed strategy once or not at all. And so we could roughly, very roughly split them into 2 different categories, which we call explorers. These are people that like to change often. Often they wanted to join the bots in the minority. And sometimes when we guess when they felt nothing was really happening, they'd just try and change strategy to see if they could make the group also do something. And then non-explorers who only switch strategies once or twice, and often right at the end, so that the group could reach a consensus. And I think the key point here is, with an agent-based model, this is really telling us we have to keep in mind heterogeneity in the population, because even with the exact same game or the exact same structure, people will just decide that they'll do different things.
Were there a significant number of people who just would not switch at all?
No, I think I have to go back to check the numbers, but probably about 10% or less. So there were more or less some people would try and change at least once.
So that left-hand bar was sort of dominantly people who would flip at least once.
Yes, at least once, and often it was right at the end. So
they're driving for consensus.
yeah, so like maybe they're the last holdout out of all the players, and so right at the end they switch, and then the game ends, and so it's recorded as a single. Okay, so what I just talked about was the kind of qualitative overview, and so we performed some statistical analysis, and we found the presence of 3 variables that influenced people's decisions at each round. The first is coordination, so people adopted the choice that was in the majority among their playing group at the previous round. It's consistent with this game theoretic model I talked about, where people try and go with the majority strategy. But we also found that people typically like to stick with their own decision, even if it kind of didn't make sense from a purely monetary point of view. And conversely, sometimes they were very sensitive to changes in the group trend. So even though Tau was in the minority, the moment there was a sort of upward tick in the voting of Tau, some people like to jump straight on that.
And were there any differences with the experiments that you did with the people sort of?
Yeah, so we actually found there was no real statistically significant difference. So we don't know whether we didn't have enough power to detect it. And maybe if we ran more trials, we would find something, but yeah, it was hard to, at least we didn't get the result we were expecting, which is sometimes the case with experiments. So one thing I will point out, which was interesting, I sat in some of those games, and most people, even though there are name tags, they didn't look up. They all just kind of like stuck to the screen, and so maybe there was no like actual effect, or we had to make the effect more pronounced.
Sorry, one other thing. Did they know each other?
That I'm not too sure, because the person that ran the experiments was a PhD in psychology in the Netherlands. I believe that they do share classes, because I think we recruited them from the marketing student class pool. So there might be a case that they knew each other, and maybe that had an influence. Okay, so having, I guess, identified these additional 2 mechanisms of inertia and trend seeking, we went about trying to incorporate that into the model. And one reason we selected the game theory approach is it's quite straightforward to introduce these new mechanisms into the payoff function without changing let's say, the fundamental structure of the model. So the way to do that, it looks kind of scary and complicated, but the first term is the coordination term I've already talked about. This is another way to rewrite it. It's more compact. But yeah, it's what I've talked about before. Individuals get a higher payout for adopting the strategy selected by the majority at their current time step. The second term is the new term, one of the new terms, inertia. So individuals get a higher payout for keeping their current strategy. You can even think of it as they're playing a game against themselves, which is usually avoided in game theory, but here we've included it. And the last term, there's some complicated function here, but it captures the trend-seeking notion. Individuals get a higher payout for adopting the strategy that has increased in popularity over the previous time step, regardless of if it's in the majority or not at the moment. And with these new terms, there are also coefficients that we had to insert, which captured how much individuals preferred, or how much they weighed each of these 3 terms. So BI, KI, and RI. And then there was, of course, this bounded rationality parameter.
Sorry, Ben, I just need some notation. Is this a dot product that we're looking at here?
This is a row vector and a column.
Okay,
vector.
so it's just the dot.
Yeah, sorry.
Okay, so there's some factor S, which is kind of like a weighting.
So no, this is the strategy. So it's S is 1 or 0.
Oh, I'm sorry. Okay, yeah, okay.
Sorry, yeah, I wasn't sure how much time to spend on the notations. Yeah, my apologies. So S is
Yeah, sorry, yeah.
S is either 1 or 0. And so if you replace that here, then this is a row vector, a column vector, you get yeah, so it's not product, and that gives you the payoff.
Okay, thanks. Yeah, I see. And then how do you, the trend is typically over multiple time periods, but you're trying to retain the Markov structure. So how do you do that?
Well, it's not Markov anyway, because there's a t-1 here.
There is a T minus one.
Yeah,
Okay.
so we debated, like, is it just let's say, this is effectively the first derivative.
Yeah, no, I'm with you there. Okay, thank you.
Maybe we thought about making it more complicated, where you remember the history of, let's say, trends, but we felt that was, yeah, we wanted to keep it simple for the parameterization step, which comes later.
Sure.
And just as a side note, we did end up analyzing this type of model by, and we could turn it Markov by making it, by doubling the dimension size of the system. So there was like a little trick that we were able to do.
Just add the previous terms. Yeah.
All right, so we obtained the parameters, these 4 parameters from the experimental data, and what we actually did was impose that these 3 summed up to 1, so we reduced the degree of freedom by 1, made it easier for us. And here are the parameters we obtained for the different types of players. Surprisingly, the rationality was pretty much the same. The tendency to coordinate was also the same, and the main difference was that the explorers had very low inertia and very high trend seeking, and the non-explorers had a lot of inertia and low trend seeking. So that was relatively interesting. So here's what let's say the updated model looks like. The circular dots are the normal agents, and the diamonds represent the committed minority, or these bots. So you can see at the start, there's a very small uptake of red strategy, and often when they change to the red strategy, they change right back because the payoff for blue is still higher, since most players are playing blue. At the moment, this is an all-to-all graph, so I haven't introduced a network structure at the moment. Later on, I'll do so, but there was a tipping point, and then there's a very rapid diffusion to the all-red strategy. So that's kind of the S-shaped curve we talked about, but now you can see it as an agent-based model.
Excuse me, what's the difference between diamonds and circles?
Oh, so the circle, the players in the circles are the normal players that can switch between blue and red, and the diamonds are the ones that stick with red the whole time. So they were these committed minority bots that only selected the contagion. Right. So the key findings that we obtained from the model is that diffusion is always fast and explosive, independent of other factors, and it was because of this trend-seeking effect. And we found threshold effects when the population had either 25% or 19% of these committed minority individuals. So I'll give a bit of an interpretation for this result. It's a heat map where the color intensity is the time it takes for diffusion to occur. On the x-axis is the fraction of the population that are the committed individuals, and the y-axis is the fraction of the non-committed individuals who are explorers. So this is a breakdown of the overall agent population. So when you're above 25% of the committed individuals, you'll always see rapid diffusion within the simulation time window. When it's below 20%, doesn't matter what the rest of the population is structured like, you'll never see diffusion. We ran this out, I think, to 10,000 time steps. And then between about 19 and 25%, you could observe diffusion depending on whether you had enough explorers or not. So that's intuitively, if you're a committed minority, you want more explorers, and then you'll be able to observe diffusion in the population.
clarity, so the committed minority are the bots, basically, it's,
They only picked the red strategy.
yep. Have you or anybody else explored, bots for the opposing?
Not with this model. So there's another model I worked on, which is competing contagion models. And yeah, so in that case, I've worked with that model on, let's say, like having fractions of both, but not for this game theory. Right?
Yeah, cool.
Okay, and I guess what was quite interesting is there was a science paper by Santola a while back, and that paper actually motivated us to design these experiments, and they also found a tipping point at 25%. Whether that's coincidence or not, probably too early to say. Okay, so I guess the last thing I want to point out is this particular project really taught me the importance of, for agent-based models, to look at both agent and population-level data, and both need to be consistent. So here are two other existing sort of classical models, and they could either get the population-level dynamics correct or the individual-level dynamics, but not both, because they missed out on the inertia and the trend-seeking term. Okay, so that was, let's say, the more detailed thing. Now I'm going to try and race through in about 10, 15 minutes on a couple of other projects that all start with this type of network model, but we look at different types of problems. Yeah. So one thing that we can do is to do some theoretical analysis and identify analytically the existence of tipping points. So those results I talked about were numerical simulations, but we can, as I mentioned, derive analytical expressions. So one of the things we did was to simplify the model that involved inertia and trend seeking, and derive some thresholds for when to expect rapid
For
contagion.
$68 a night. What do you get with a suite that you don't get with others?
So what was it?
Well, it's probably worth it, don't you think? That's why you're ringing, isn't it?
There we go. Right, they're muted now.
Okay. I was wondering. So we identified when there was rapid contagion spread as a function of how many committed minority in the population, how sensitive individuals were to trends, how much better the contagion should be, and the density of the network. So in this particular case, we did allow for some network structure. So the theorem would look something like this. If alpha is the advantage of the contagion over the status quo, and zeta is the fraction of committed minority, while k is the number of neighbors for each individual, so we'll assume some homogeneous network structure, then the status quo remains if alpha is less than this particular value. Rapid diffusion of the contagion occurs if alpha is greater than k minus 2, and if alpha is between these two values, then diffusion will occur if and only if the number of committed minority exceeds some threshold zeta star, and there's some complicated formula for that as a function of k and alpha. So that's the type of analytical result that we can derive. But in the interest of time, I'm going to forge ahead. The next question we can ask is, how does the network structure facilitate or impede social contagion spread? And so those that work in network science will know there are different classes or structures of networks. Some are scale-free, where there are a couple of nodes with very high degree, and others have low degree, and other structures known as small world networks, where there are high clustering, like highly clustered communities, and low path distances on average between nodes. So here's a plot of the number of committed, or the fraction of the committed of the population that need to be committed minority in order to observe a certain percentage of successful contagion spread over a certain number of simulation runs. So what that says is, when you cross a particular threshold, you'll go from observing 0 simulation runs with successful contagion spread to almost all the simulation runs having successful contagion spread. And in general, what we found was that the lower the average degree, so the sparser the network, the faster the contagion spread. And the higher the clustering, the more likely we could observe contagion spread, but it would also slow it down in a sense. The next thing we looked at was where we wanted to place these committed minority individuals in the network to facilitate the spread of social contagion. I think you can all kind of see where or why this might be motivated. And the way we approached it was to look at network centrality. So intuitively, centrality is a measure of how important nodes are in the network. And if I showed you this example, my first reaction is that node 4 is the most central in the network. But that's a little bit more involved because there's different ways to define centrality. And depending on which centrality you pick, these nodes have different rankings in terms of what's most important. So we placed the committed minority at the nodes with the highest centralities, and we compared the different centralities. And what we found was there was a centrality called the Bonacich centrality that was the most effective, and there's some factor that you use to compute it. But the way to interpret this is that to spread social contagion, you want to place these committed minority at the nodes that have the most access to other isolated individuals. So you don't necessarily need them to place them here. In fact, in this example, you'd actually place the committed minority at node 2 because they have access to one individual in another who, in a sense, are more isolated or have fewer other connections.
What is Bonacich?
It's so if do you want me to go into the details? Maybe. Yeah, maybe talk about it.
Is this related to the age that you get unconnected components?
I'm sorry, just say it again.
So isn't this related to an age when so that it's critical when you delete it, your graph is not connected?
I haven't thought about it from that perspective, but so I'll maybe briefly. Actually, I'll skip the feedback control part because. So the last thing I want to talk about is simple versus complex contagion effects, which I promised you right at the start of the talk. So when we were developing the model, we made certain assumptions about these agent dynamics, which in this case was that they were playing a game, or we could capture what they were doing by some game with some payoff functions that where they wanted to coordinate. So a simple contagion is a different class of models where the effective influence from one neighbor is independent of the effective influence from another neighbor. The easiest example of this is an infectious disease like COVID. If I'm in the room with one infected person, there's some probability I get infected. And if there are 5 infected individuals, they each have some independent probability of infecting me to a first approximation. So these effects sort of stack up. And if you wanted to look at this mathematically, the probability of me being infected with the contagion as a function of the number of neighbors, that's the type of curve you get from a simple contagion model. The complex contagion model, which is what I really have focused on over the majority of this talk, is, as I mentioned before, social influence effects are not independent, and that's the type of curve that you would get instead, where you might go from a very low probability to a sudden jump in probability of being infected by the contagion. And perhaps it's no surprise that when you have these simple but important differences in the way agents work at the agent level, you can have very different population level predictions. And a very good example of this is with simple contagion, the denser the network, the faster the contagion spreads. That's why COVID's a problem in urban areas. But for complex contagion, as I just mentioned, often you get faster spread in sparse networks because I guess the influence of each neighbor is much more important, more powerful. So one question I've been really interested in to ask is information a simple complex contagion? Because I read a lot of papers that use both. types of models to approach information spread modeling. And the talk has to date mainly focused on behaviour, which is social conventions, but so misinformation is another, I guess, key focal area now. So in the form of a tweet or a news headline, will it behave like a simple or complex contagion? And so what we did, and so Toby is in the room, and we, together with Nick Bradley and Uli Ecker from UWA, we ran some experiments where we asked participants to whether they'd like to share or not 36 headlines on various topics, and we manipulated the sharing metric. So this is one type of headline that the participants saw, and they could either say, yep, I'll share it, or no, I won't share it. And what we manipulated were the metrics that they saw to try and capture at least some sort of social influence effect that you might typically observe in, let's say, Twitter or other social media platforms. So this was typically kept constant, and then we changed this particular number within an experiment. We ran 3 experiments where this number was also different between them. So we had 10, 100, and 400. And so within the experiment, the headlines changed in terms of the shared by. All right. So what we found was a statistically significant but very small effect on how the number of past shares, or the sharing metric information, influenced the probability the participant would share. It was much smaller than the existing models, and this is what we actually observed from the data. So here's the simple contagion model, here's a complex contagion model, and the sharing probability is almost always 20%. There's like a small 5% increase, but in the grand scheme of things, it doesn't actually matter that much. And so there are key differences in population level predictions. And now our work is on other factors that influence sharing, like repeated exposure to the same content, the type of information, individual differences, and maybe differences in platforms. All right, so to quickly conclude, I've talked about some network models where we've got agents that interact, and we can use it as an abstract way to study social contagion spread. The model that I worked on mainly was a game theoretic model, and we looked at how it could be used to study social convention change. Then I briefly talked about the different types of problems we can study with the same class of models. And I guess the key conclusion is that information and behavior are both contagions of interest, but seem to be, at least, have some fundamental differences in how they work at the individual level. So an ongoing project is to continue gathering empirical evidence to help understand, what type of models we should be using. Current and future work, I want to look at recommender systems, so incorporating the way content is recommended to people, which is what happens in social media, models where agents have distinct belief in behavior states. Theoretical analysis, mainly on optimizing the network structure to help contagion spread, and as I mentioned before, looking at introducing a competing contagion to stop the spread of the contagion of interest, and lots of experimental stuff going on as well. All right, sorry for taking so long.
We have time for 1 or 2 questions.
Have you considered kind of negative impacts? So, for example, I don't like you, and so because you've chosen to adopt a contagion, I decide completely the opposite.
I guess there's 2 answers to that. The first is I'm not let's say, as knowledgeable about the experimental evidence for when this type of backfire effect happens. From a modeling point of view, it's relatively straightforward to incorporate. So the game theoretic model I talked about, another word for that is called coordination games on networks. So these players coordinate with each other. And to model the backfire effect, you can change that to an anti-coordination game. So then you want to avoid whatever is happening in the majority of your neighborhood. And you can make that even more complicated by asking players to play anti-coordination against some neighbors and coordination with others.
But you want to kind of also incorporate sort of the network, you know, so not just the network structure, but also the network positive, negative.
Yeah, so the way to do that would be, for example, I could try to anti-coordinate with you if I don't like you, and then I could coordinate with Lewis if I liked him. So then I'd be playing games where the payoff would be different according to the edge that I'm connected to with the neighbor. So there's a whole bunch of work on these mixed coordination and anti-coordination network models.
I guess, could that be relevant for the experimental evidence where you were sort of seen by this many, shared by that many? Is there a difference in the real world on Twitter where people know that it's their friends who have shared versus where it's just a number that isn't connected?
Yeah, so I think the next thing we're thinking of doing is, so Toby is involved in something called the misinformation game, where it's like a much more advanced social media simulator, and you can manipulate these types of things. I think what's hard is to get participants to be invested in like hating some mysterious person that they're only exposed to for the duration of the experiment. But you know, Toby's an expert on that. So.
On the Russian withdrawal example, maybe some people would say that's not very believable, so you wouldn't get much sensitivity. Have you explored that? Like if something seems a bit more believable to people, yet still bogus?
Yes, so I think in general, most of the headlines just weren't shared as much. So what we found is people in general didn't like to share things often. Again, so I think Toby's actually done some experiments where they specifically asked about believability of certain headlines. In that experiment, we never really quizzed them, so we're not really sure if there was some type of effect.
Yeah, I guess that was, maybe you'd see that if there was some variability in the levels of response from, you know, that was like 20 going up to 25 or something.
I mean, so Bradley analyzed it based on true and false,
Yes.
and there wasn't a difference between the true and the false. So we had some true headlines and some false headlines, and their sharing was very similar.
Similar.
So in a separate study, where we used a very similar set of headlines, their belief ratings were higher for the true, so they could discriminate between them based on truth and false in terms of belief, but it didn't seem to impact their sharing.
I think what, I mean, Nick has really been leading a lot of the work on this, but it seems like whether people share things, it's not always whether they believe it. So believability and transmissibility is actually, they seem to be maybe related, but quite independent features of the information content.
So is that 20 to 25 considered a sort of a strong signal? Because I mean, even a small change could have big network effects, right?
Yeah, so sorry, do you mind just elaborating what you mean by a strong signal?
With epidemics, you know, where you get these kind of exponential growth effects, like here, a small change in sort of something can lead to big effects after a few steps in time.
Yeah, no, so in this particular model, I don't think that changes. And that's partly the reason why, you know, we're saying it seems like people just have some fixed probability or some reasonably constant probability of sharing every time they encounter the headline. So is it the fact that maybe when things go viral, the recommender system's pushing you to encounter it more often? Maybe that's actually what's driving some of the spreading dynamics.
Oh, it's too quick. Well, look, no one's kicking us out. Like, you know, look, maybe let's thank Ben one more time. And if you but yeah,
I was just going to ask about the heterogeneity of the strategies.
Yes.
I mean, you've identified two, but I'm guessing there's a lot more underneath that.
Yeah.
So, I mean, that's a good start, but have you looked into potentially some other types of strategies that might differentiate in the population a bit more?
No, we haven't really looked into it. I think we picked two because it was what we could feasibly try and use to parameterize the model.
Yeah.
And I guess for me, I didn't feel confident enough to go beyond that because we only had 180 participants.
Yeah.
Maybe if we got more participants and we could see some, you would have more power to identify other types of strategy. I think in hindsight, we'd also probably try and debrief the participants. We didn't actually expect there to be this much type of difference in the way people played. So yeah. maybe that was a bit naive of us.
Well, you know, you talk to most people who work in individual differences and they'll tell you to expect that.
Yeah.
It would be really interesting to see what those strategies are though, and how much insight people have into what they're doing.
I think what surprised me the most was people generally played very fast. So we gave them a minute per round to decide, and most of them picked in 10 seconds.
Wow, okay.
So it was like it seemed they were quite intuitive, or they're just, maybe there wasn't enough money on the table. But more or less it seemed like they were playing intuitively or responding as fast as they could.
Just a quick question also about the models. So, what do you think about cell biology models where cells send signals and they communicate, and also there is a kind of points where then suddenly change the situation? So I was thinking about also these models. Are they applicable or are they totally different?
So I probably don't know enough to make a very well-argued judgment on that, but I guess my experience with the last problem was, even for something like epidemic models, where it's quite intuitive to think that information might spread like an epidemic process. It seems that we have to be very careful with where we're borrowing models from or which framework we're using, because you know, in social populations, there's so much depends on the context. And we need to really be careful, you know, if we go between contexts, we don't bring in assumptions from, you know, that context, and then the model doesn't really work as well as we'd like.
Yeah, because cells also rely on their neighbors when they make decisions. That's why I started.
Yeah, I mean, I'm sure that there's some like, network phenomena involved. It's just whether the way cells interact with the neighbors is the same as it happens in social conventions or in information spread. That's probably the question to ask.
All right, let's leave it there. If anyone wants to lunch,